Testing. Looks good. All right. Good morning, everyone. Good morning. Happy Father's Day to all the fathers out there, and to our Heavenly Father. How are y'all doing today? Any visitors? Anybody new? Hello. Feel free, if you want, to say your name and where you're from and how you heard about this class. Awesome. Welcome, Charlie. Anybody else? I think I recognize most people. All right, let's get started this morning. As you may have noticed, I'm not Ross Hoagland. My name is Tim. I've been in this class for a while now, and I love it. And I'm here to give some announcements. So we have Hugh with us through July 16th. So we have Hugh for a while, which is fantastic. And then we're going to have a series on Bible prophecy, July 13th, 30th, and August 20th, with Mark, Ted, and Ken Samples, right? Awesome. Looking forward to that. And then Hugh will be here all the Sundays through September 24th after that. I don't have a joke for you this morning, but I do have some scientific research, which I think matches this class a little more. Sorry, Ross Hoagland. So last Sunday, I asked Hugh Ross a question about the vagus nerve, and he told me to come back with a research response to that, and I found some very fascinating stuff out there on the scientific literature. So first, I want to restate my question, because my question wasn't actually specific enough. The true question is, why does our recurrent laryngeal nerve loop around our heart before coming back up? It takes a very inefficient route. This is often touted as a bad design and evidence for evolution, right? So basically, we have a vagus nerve. It doesn't travel through our spine. It splits off into two and comes down either side of our neck and then innervates all sorts of parts of our body. Now, the vagus nerve has on each side two branches, the laryngeal nerves, feeding our larynx. That's why they're called the laryngeal nerve. Our larynx is our voice box, what allows us to talk. The upper one, the superior laryngeal nerve, goes straight from the vagus nerve to our larynx. Very simple route. That makes sense, right? So the evidence for bad design, supposedly, is that the bottom nerve on either side travels all the way down, about over an extra foot of length, travels all the way down around the aorta, loops around the aorta of the heart, and then comes all the way back up, only a couple inches from its starting point, to then innervate the larynx. And it does this on both sides. On the right side, it loops around the subclavian artery coming off your heart. On the left, it goes down even further and goes around the aorta. So why does it do this? Well, there are some possible answers without looking at scientific literature. So maybe this nerve, as it's coming back up, gives sensory data to the nerve endings at the larynx. There's known to be pressure sensors along the way. So perhaps taking a circuitous route back up allows it to gather data from below and give it to the larynx. But for me personally, that wasn't completely satisfying of an answer. Because you can have just a third branch just, collecting data from below. Now, in 1983, there was a scientific paper published that suggested that the laryngeal nerve, the recurrent one that goes down, not only provides nerve function, but acts as a mechanical support for the aorta and its other arteries. Now, this was in 1983, and there wasn't a lot of data on this, because it's very invasive to go in, poke around, see what nerves you have, where they're going. So there wasn't a lot of data, but 40 years have passed, and a lot has happened since then. But before I go into that, I just want to clarify one thing about the circulatory system. You have to understand this before I go into the answer. So in our circulatory system, right, blood goes throughout the body delivering oxygen, and it comes back, deoxygenated blood, and it comes to the heart. The heart then pumps it into our lungs. Once in the lungs, we breathe in, we oxygenate the blood goes back into the heart, and then is pumped back into the body. So on the route of a blood cell through the body, it makes sort of a figure eight. It passes through the heart twice on its route. But when we are in fetal development in the womb, we aren't breathing. Our lungs are filled with fluid. We get our oxygen from the umbilical cord, us and every other tetrapod on Earth. This is every organism that's more advanced than a fish. So with no reason to breathe in our lungs, there's no reason to pump blood to them too. So we form what's called the ductus arteriosus. This is basically a shortcut. It bypasses the blood going into the lungs. And this forms in fetal development. So blood is not pumped into the fluid-filled lungs. There's no reason to. So it just bypasses that and goes right back into the heart. Of course, you can't have this as soon as you take your first breath. It's now inefficient to have this bypass, right? So it must close off. Now, it turns out that the laryngeal nerve looping around the aorta actually helps separate it from the pulmonary artery below. And what happens when you stretch out a stretchy tube, right? What happens? The tube, as it stretches out, gets smaller, it gets constricted. And so the nerve, at this point in development, acts as a mechanical sling to help stretch out the ductus arteriosus, develop elastic fibers within, toughen it up, so that it eventually turns into what's called the ligamentum arteriosum. So this duct, this artery, literally turns into a ligament over time. This was suggested in 1983. Since then, we have a lot of data to look at. So I found a peer-reviewed study from 2017. This was a review. It was looking at 53 different studies, tens of thousands of patients, right? They found that around 0.5%, so not very much, like 1 in 200 or so, the right recurrent laryngeal nerve will not go all the way down. And they found that if it doesn't go all the way down to support the subclavian artery on the right side, you have an aberrant subclavian artery every single time. So in people where the bottom one just goes straight to the larynx, their subclavian artery doesn't function the same way. It actually develops, comes up, goes behind the esophagus and comes back down. And a lot of these people present symptoms like trouble swallowing, dysphagia. So you say, okay, Tim, that's the one on the right side. What about the even crazier one going even further down the aorta? Well, throughout all literature, there have only been 6 known cases where the left one didn't go all the way down. And in every single one, the patients had cetus inversus, which is all their internal organs were flipped, were mirror image. So really, in every single case, that was almost basically the right one, but because their heart is now on the left side, their heart is on the right side, right? It sort of is the right one. Does that make sense? So really, taking out all the cases where there's been the cetus inversus, there's never been a human that hasn't had their recurrent laryngeal nerve loop around the aorta. There's not one case in all of human history. And I think that's evidence that it's there to provide mechanical support to stretch out the ductus arteriosus during development. And I think there's a reason then this recurrent laryngeal nerve is found in every single tetrapod, even giraffes. So a giraffe with a neck multiple feet long, its laryngeal nerve travels all the way down, like 5 or 6 feet to its heart and 5 or 6 feet all the way back. And it's possible that it kept that because it needs it during development to turn off the ductus arteriosus. And so I just wanted to present that to you guys, that sometimes when you look at the function of a specific part of the body, like this nerve, its function might not even be nerve related. Here we see it's a mechanical sling. That's something you almost never see nerves doing. So I just want to present that to you. This is seen as an evidence for evolution, for bad design, and I just wanted to come to say to you that just wait and see. We've already seen over 40 years, there's more evidence that this thing is here for a reason. And I think for all the skeptics out there about this, just wait and see what the evidence says, because I think as we go on, we'll find more and more reason for design in so many of these anomalous anatomy parts. Anyways, thank you. So I'd like to welcome up Dr. Hugh Ross, continuing his talk on fine-tuning. Thank you,
Okay.
Dr. Ross.
Well, you're very welcome. And hey, if you participate in this class and you ask a really hard question, don't be surprised if I give you an assignment. And I knew Tim would deliver. I mean, wasn't that just wonderful what he shared with us? So, and it was right in line with what we've been talking about, how pervasive throughout the sciences, we get these non-theists claiming, this isn't designed by a good God. Look at all the bad designs. But if you actually do a little bit of research, inevitably you discover what people call a bad design turns out to be an optimal design. In fact, it just reveals the glory of God all the more. Okay, we're in a series on design for redemption, and it's basically a series where we're looking at how the realm of nature is fine-tuned, not only to make possible the existence of life, but make possible the existence of human beings. And not just a few of us, but billions of us, and designed in such a way so that billions of us can be redeemed from our sin and evil and enter into an eternal relationship with the Creator. You know, in launching this series, people have asked me, well, Hugh, how many books have you written on fine-tuning that testifies about God? I was rather shocked. 7 books. So the latest one is Designed to the Core, and much of what you're hearing is from this book, Designed to the Core. But we've been doing the past few weeks is saying, look, before you present this evidence for design, it's crucial to first deal with all the rebuttals that you get from non-theists about why we think this is design. And I'm not going to go over this in detail. Every one of these paradoxes class is video recorded and archived, so you can go to paradoxes.org, and we discuss the very popular puddle analogy. Just like any old puddle will do for water, they're claiming any old universe will do for life. And basically we made the point, well, wait a minute, life is not like liquid water. It can't adapt to any old puddle. We looked at the multiverse, life as we don't know it, the sample size. Right now we're on the last one, bad designs. And so you just heard from Tim. People were looking at the human body and saying the appendix has got to be a bad design because it doesn't serve any purpose. Well, because it's part of the digestive tract, they thought if it had purpose, it's got to play a role in digestion. It doesn't play a role in digestion, but it plays an important role in the human response system. And then Tim had the audacity to say, what about the vagus nerve? And so I said, well, go research that. And, you know, I do remember reading that paper you talked about, but that's 2017. I mean, that's 6 years ago. And I said, Tim, I don't remember the details of that paper. And rather than give you a guess, I want to have you give an accurate answer. And didn't he do a wonderful job? Rudy gave us an accurate answer, but it's an example. People were looking for function in the vagus nerve. It does serve a function in terms of the nervous system, but people were not looking for the fact maybe God designed it to serve 2 functions, maybe even 3. But Tim showed us, hey, it provides mechanical support in a way that's crucial, particularly, I mean, when it talks about tetrapods, these are animals that have got 4 limbs. This is anything more advanced than a fish is in that category. And they have a developmental complexity that does require that you have different designs for when it's in the womb and then when it comes out of the womb. Same thing for the reptiles in the egg. Okay, what we've been reviewing here is that whenever you hear a charge, this can't be the handiwork of God because it's a bad design. 2 questions. Have all possible design purposes been exhaustively examined? Before you call anything a bad design, and by the way, I think this is true for us human beings, right? Before you think, hey, this human being doesn't serve any purpose, well, God's got multiple purposes for each one of us. And by the way, he designed every human being to fulfill a different set of purposes. And so look beyond the obvious. And then have all possible design trade-offs been considered? And so, people, I mentioned the example of the backbone last week. Our backbone is not optimal if all you're going to do in life is sit. It's not optimal if all you're going to do in life is sleep. It's not optimal if all you're going to do in life is run. But it is optimal to allow the human body to walk, run, sleep, sit, stand. It can do all those. And it can't do them all perfectly, but it's just like buying an automobile. You can't buy an automobile that gets 50 miles to the gallon and has the performance of a race car. You can have some of that, you can do trade-offs, or you can emphasize one against the other. Well, I was making the point last week that typically the charge of bad designs, you find it in the complex sciences, in the life sciences. And where things are so complex, it's very difficult to see all the purposes that are there. But now it's even creeping into the simple sciences. People always ask me why I became an astrophysicist. Because in astrophysics, you're dealing with material that's so simple, it's relatively straightforward to develop a set of differential equations or partial differential equations that describes with some precision the activities going on there. I mean, we just had a conference a couple of weeks ago, or a workshop at Reasons to Believe, on human exceptionalism and human origins. And, I was joking with the anthropologist there is that, mathematics is a great tool in astronomy. It doesn't help at all in anthropology. You just simply can't develop a set of differential equations. I actually tried to do that when my sons hit their early teenage years. Can I come up with a set of differential equations that will predict their behavior? It does not work. For all you fathers out there, as your children begin to hit their teenage years, forget about trying to develop equations to predict their behavior. They're way too complicated. But what is a shock to me is recently in the scientific literature, there have been non-theists basically making a charge that we're seeing bad designs in the simple sciences of physics and astronomy. And in fact, there have been papers published saying planet Earth is a bad design because we can conceive of what they call super habitable planets. And again, I'm not going into the details. This all got recorded, so just blast through this, that they're making the claim that life would be a whole lot better here on planet Earth if we had a smaller star, a larger planet, greater tidal forces, a moister, more oxygen-rich atmosphere, large shallow sea areas, and smaller and more numerous continents. This would make life a lot better. And this is a classic case of design trade-offs. Yes, a smaller star will burn longer. The smaller the star, the longer it will burn, which means you've got a longer period potentially for life to exist. But overlooks the fact that if you go with a smaller host star, you get greater flaring activity. Our star, the sun, has the minimum flaring activity of any star that we know. It also has the maximum luminosity stability. You go with a smaller mass star or a bigger mass star, you're now going to be orbiting a star that's got greater flaring activity and greater luminosity and stability. You say, well, what happens when you've got greater flaring activity? Well, it's going to knock out your GPS satellites on occasion, which, as I said last week, my sons both declared that would be the end of civilization as we know it. Or it winds up knocking out your power grids, which I think a lot of people would realize would be a significant hit to our civilization. Now, the upside is you get to see really spectacular aurora. By the way, if you've never seen, how many of you ever seen the aurora borealis? Okay, lots of you have. That's good. I actually got to see it here in Los Angeles in 1989. That's when they had a major flare so powerful it knocked out the Quebec power grid. But it actually caused a big red blob to show up in the night sky here in Los Angeles. The only time I've ever seen it from Los Angeles. There's a possibility, but it looks like the next solar maximum is going to be quite a spectacular one. So there may be a chance that there'll be a flare that you can see there. But now the Quebec power grid is protected, but not the other power grids. Only a few are protected. So, and incidentally, I remember one night I was on the telescope in Canada, and we had an auroral display. It was so bright we couldn't see stars. It was moving. It was all different colors of the rainbow, and it was moving rapidly across the sky. and we kept waiting for it to end so we could actually do our astronomy. It never ended. It lasted all night long. So a lot of you think it'd be wonderful to see the aurora. I can tell you, a lot of astronomers in Canada, they curse the aurora when it shows up because they just can't do their astronomical observations. But yeah, a smaller host star, as we mentioned last week, is not a good thing. You've got to bring your planet closer to the star in order to keep it warm enough for liquid water, but that makes it tidally locked, where basically it's rotating about roughly the same rate that it revolves around the star, which means daytime would be lasting weeks and months instead of just hours, making it blistering hot in the daytime and freezing cold. Okay, smaller host star. And they said, well, a larger planet gives you more living space, but it also gives you a thicker atmosphere. You get deeper oceans. The internal heat flow is too low. You're not going to have the plate tectonics you need. You're not going to have a strong magnetic field. It's going to be a less dense planet, which means you're not going to be able to mine the resources that you need for advanced civilization. And the asthenosphere, the thin viscous layer that separates the crust from the mantle, will be too deep. And when it's too deep, that means the plates on the surface aren't going to move very well to one another. It shuts down the plate tectonics. And also, when you go with a planet that's smaller, you've got less aluminum. And as we mentioned last week, you need the combination of water and aluminum in contact with one another to make sufficient talc. You want to know why the crustal plates move so efficiently against one another and slide underneath one another? The combination of liquid water at a certain density, along with an abundance of aluminum, makes talc and other lubricants that actually allows the plates to slide relative to one another. And those of us living here in Southern California, it also minimizes the number of magnitude 10 earthquakes. I mean, kind of the maximum you're going to get here in California is a magnitude 8, which is survivable. Magnitude 9s and 10s aren't very pleasant. So, and, you know, believe it or not, you're at a greater risk of earthquake damage if you live in Missouri than if you live in California, or if you live in the state of Washington than you live in California. Because of all the faults we have here in California, I mean, the joke is that California has lots of faults in both senses of the term, but because of all the crustal faults we have, the earthquake energy can't travel that far, and you can't get earthquakes that are very intense. But in Missouri, you can get a magnitude 9 earthquake. They had one in the 19th century. It rang all the church bells in Boston. And you can have a magnitude 9 earthquake in Oregon or Portland. You don't get them very often, but when you do, it's bad news. Okay, the one thing we didn't get to last week is the problem of a moon. Now, the reason why these astronomers said we'd be a lot better off with a bigger moon, you get stronger tidal forces. The tides would be bigger and they'd be stronger, which means you get a more efficient recycling of nutrients on the continental shores. And off of each continent, you got what's called a continental shelf. Basically, what happened during the Great Unconformity is there was a massive tectonic event that caused huge landslides off the continents into the ocean, and what that did is it produced these shallow continental shelves, basically regions off the continents, off all the continents, where you got water of relatively shallow depth, an ideal environment for all these organisms that live in the ocean. Life is much more productive in a shallow sea than it is in a deep ocean. There's more oxygen, there's more sunlight, and so this is where we get an abundance of life. This is where we draw all of our marine food supplies. And so they're saying we'd be better off if we had a bigger moon, because it would actually cause the recycling of nutrients to be more efficient there, and we could have a bigger food supply there. But there are problems with going with a larger moon. If you go with a larger moon, your planet will rotate more slowly, because here's planet Earth, here's the moon, and the moon's gravity on the near side of the Earth pulls a little harder than it does on the far side. And the difference in those forces acts as a brake on our rotation rate. And so our planet rotates more slowly every year that goes by. Are you aware your day is getting longer? You got more time to get work done because we have a longer day than we did in 2022. But it's only a few microseconds longer, so it's not going to help you perform a lot more. But over time, that adds up. So for example, 150 million years ago, we had a 23-hour rotation rate. Now, when Theia and the proto-Earth collided to make a bigger Earth and produce the moon, that's the origin of the moon. The only way you can get a big moon orbiting a small rocky planet is if two rocky planets collide with one another, where the bigger planet's got a really deep ocean. Planet Earth started off with an ocean thousands of kilometers deep that cushioned the collision enough that you basically get a merger event and it produces this gigantic moon. Now, if the proto-Earth and Theia were bigger than what they were, you would get a bigger moon. But if you get a bigger moon, that means it would slow a rotation rate down too quickly. And so that collision event basically produced a planet Earth with about a 2 to 2.5 hour rotation rate. So we were really spinning rapidly. Earth was the fastest spinning planetary body in the solar system. That kind of collision basically greatly sped up the rotation of the Earth. But thanks to the moon, that 2 to 2.5 hour rotation rate has been slowly getting longer and longer and longer, where today it's 24 hours. Now, make the moon bigger, and then by the time humans are able to come upon the terrestrial scene, we cannot live on planet Earth until planet Earth is 4.56 billion years old. There's a variety, in fact, we'll be going into that in this class, why it is we humans cannot survive on our planet in less than 4.56 billion years. But it's crucial that when the time window opens for humans to exist on planet Earth, we have a rotation rate that's going to make possible global civilization. You say, well, what's wrong with having a 25-hour rotation rate? You got a bigger moon, you got 25 hours, we get more work done during the day, you got more time to sleep at night, right? Well, what are the consequences of having a longer rotation rate? It means that the temperature at 2 p.m. is going to be hotter than it would be with a 24-hour rotation rate, because you got sunlight. You probably notice this, as the sun is shining, it gets warmer and warmer and warmer, and you get the maximum temperature around 2 p.m. But if it's a 24-hour rotation rate, instead of it being, say, 90 degrees at 2 p.m., it's going to be 96 or 97 degrees. Or if you pick a really hot place like Phoenix, their summer temperatures get up to, 122 degrees. Now it gets up to 130, 135 degrees. Okay. I've actually personally have had the experience of what it's like when the temperature gets above 130 degrees. You know, my wife and I, we've traveled around the world. We've been to Sudan. I remember we were there in Khartoum. It was 120 degrees and 100% humidity. Extremely unpleasant. We were just drinking water nonstop, but believe it or not, the hottest I've ever experienced it was not in Africa. It was not in Hong Kong or Singapore or India. It was in Canada. Canada, believe it or not. Okay. Canada's got a tiny desert. There's only one part of Canada that they classify as a desert. It's 7 square miles, basically in southern British Columbia, and they put a radio telescope in the middle of that place. So I got to spend the summer at the Penticton Radio Observatory, 7 square mile desert. Okay, but because the desert is small and because there's mountains all the way around, it's kind of like a parabolic bowl. It really heats up. So even though it's north of the United States, in the summertime, it can get really hot. Say, well, how hot can it be? Well, I was 21 at the time, and there was a really hot summer day, and the receiver needed to be repaired. And because I was young and slim, they said, you get to repair it. The rest of us can't handle the heat. So I had to go out there and get up in a cherry picker And I said, look, I'm going to need water delivered to me about every 15 or 20 minutes because it's going to be. And they had a thermometer outside. All I could tell was the thermometer was broken because the mercury went up so high. I said, what was the top level? Top level was 135 degrees. It was hotter than 135 degrees, probably close to 140. And I had to repair this thing. So, but every once in a while I would drop the cherry picker down. I would drink a liter of water. I was drinking a liter, literally about every 20 minutes. And I was able to repair the thing. But also, I got to hear a couple of farmers that were beyond the desert. They were talking to one another, and because our antenna was tilted down, and I was right at the receiver point, I could hear their conversation from 8 miles away. So I won't tell you what they said. So I wonder if they're even aware that their conversation is being listened to. So, but I'm off track. I apologize for that. But the whole point is, you don't want a bigger moon because that's going to slow rotation rate down too quickly. There's another reason why you don't want a bigger moon. This was discovered by an astronomer in Britain who said, you know, we need the moon to be a certain mass in order to keep the rotation axis tilt of the Earth stable. So, for example, Mars has 2 tiny moons. The moons are so tiny, it plays no role in stabilizing its rotation axis tilt. And so if you want to know why the polar caps on Mars are as small and as thin as they are, well, they keep melting every time the polar axis, rotation axis, tilts over. It can tilt back and forth by about 60 degrees. And so that polar cap up there, once the rotation axis tilt, it gets exposed to warm sunlight, the ice disappears, but a new pole will form because comets keep bombarding. Just like the moon has some ice at the South Pole, there's a crater there with walls so high that when comets bring frozen water there, it stays frozen. It doesn't melt. Likewise, the poles of Mars are such that when ice accumulates there from comets, it doesn't melt and it builds up, but hey, it keeps tilting back and forth. And planet Earth, because we got this gigantic moon that's not very far away, it keeps our polar axis stable to about plus or minus 1 degree. It'll go down to 22.1 degrees and it goes up to 24.5 or 24.4. Right now it's 23.5. So it moves back and forth. And it moves back and forth on a cycle of about 41,000 years. Now, that actually affects the climate. So for example, we're now going down towards 22. That's going to make our climate colder. When it goes up to 24.4, that makes the climate warmer. But because it's only a tilt of plus or minus 1 degree, it makes us slightly warmer and slightly cooler. It doesn't stop human civilization. But if it were plus or minus 5 degrees, we would now have significant climate change that would basically rule out global human civilization, and we'd have to keep migrating all the time. It wouldn't be a pleasant situation. And yes, this astronomer in Britain, I'm trying to think of his name, David something, I'll come up with it. But he said, what's interesting, my calculations show that there's a sweet spot where you get the greatest stability. And our moon is not at the sweet spot. The sweet spot would be where it had about 30% less mass. That would give us the most stable rotation axis tilt. And so what's really interesting is that the moon is at the very high end where you still have stability. He said, increase the mass of the moon by 1 or 2%, our rotation axis goes unstable. So he said, I got to figure out why. He may be a theist, I don't know. But he basically said, hey, this is design. Why isn't it at the sweet spot? Why is it at the top end where we still have stability? And he published a paper basically making the point, because it's crucial that the moon be big enough to slow rotation rate down to 24 hours during the narrow time window when human beings can exist on the planet Earth. So make the moon any more massive, the obliquity would become unstable. Make it any less massive, our planet would be rotating too rapidly. Well, I've told you the problem of having a planet that rotates too slowly. What happens if it rotates too rapidly? Have any of you ever looked through a telescope at Jupiter? Okay, Jupiter actually rotates faster than 10 hours a day. So it's 9 hours and something. And because of that, when you look through a small telescope or a really good pair of binoculars at Jupiter, what do you see? You see storms on Jupiter, but they're highly laminar. You basically see what are called the belts. So you see these storms running through Jupiter where you got these parallel belts all the way through. If you've never seen it, it's spectacular. By the way, we are going to schedule a star party, and we'll try to find a time when you can look at Jupiter. And you can always see the 4 big moons of Jupiter. In fact, if we pick the right time, you'll be able to see an eclipse on Jupiter, where one of the big moons goes in front of Jupiter, and you get to see a black spot slowly move across. Anyway, again, I'm diverting. I'm excited about astronomy. Oh, you can tell that. But the problem if we had our 23-hour rotation rate is that we wouldn't get even distribution of snow and rain. You would get these laminar flows, because if you rotate the planet more rapidly, the wind patterns become more laminar, which means that certain parts of our planet are going to get a superabundance of rain, and others won't get much rain at all. Now, it doesn't mean humans can't live on the planet, but it would make global civilization challenging, because now you no longer have an even distribution of rain and snow, and moreover, where you got the winds being accelerated, that means you get more storm activity. Again, if you were to look at Jupiter through a telescope, you see these laminar things, but you also see hurricanes. And one of the hurricanes on Jupiter, the diameter of the hurricane is about twice the diameter of Earth's planet Earth. He could literally fit 4 planet Earths into that little hurricane. You say, well, how long does it last? Well, a hurricane on planet Earth lasts, what, maybe 3 days, 4 days at the most? Hurricanes on Jupiter last centuries. Okay, so again, go back in Earth's history, you've got hurricanes and tornadoes that are more of a problem than we have today. So nobody likes hurricanes and tornadoes. We need them, actually. They do play a role in making sure that certain nutrients are distributed on the continental shelves. They also act as a thermostat to regulate the temperature of the planet as a whole. But you don't want them lasting weeks on end. And you don't want them all being Category 5 hurricanes. And so tonight, when you say your prayers, you can thank God that we live on a planet with a 24-hour rotation rate, not 23, not 25. And it's all because the moon's at just right size. So we really don't want to have a larger moon. Yes, it would have the payoff in giving you a greater circulation of nutrients on the continental shelves, but there are consequences. And so when you look at the design trade-offs, we have the perfectly designed moon. Okay, let me wrap up this idea. Well, wouldn't we be better off if we had more water vapor in the atmosphere? There'd be more rainfall. I mean, look at all the crops that you could grow in the deserts off here of California. You could have a lot of water in Arizona, grow more crops. A moister atmosphere, wouldn't that be a good thing? Well, a number of papers have been published saying, number one, water vapor is a greenhouse gas. So if you actually have a planet with more water vapor, it traps more heat from the sun. And it's actually a more powerful greenhouse gas than carbon dioxide. You say, why aren't we worried about water vapor in the atmosphere? Well, it turns out if you put more water vapor in the atmosphere, more rain comes down. But if you design the planet in such a way that its average water vapor is higher, it traps more heat. And we already know the temperature of the planet can't really go any higher. push the temperature of our planet up by another 1.5 degrees. We melt the winter polar ice cap. When we do that, we bring on the next ice age. Not a nice thing you like to have. All my Canadian relatives would be highly disturbed if we bring on another ice age. Okay. But there's other issues with a moister atmosphere. Have you ever been, I can go back to Khartoum, where my wife and I spent a week, where it was 120 degrees and 100% humidity. Moist heat is not a pleasant thing to experience. Go to Houston in July, and you'll know what I mean. You go outside, and your shirt is wet from top to bottom, literally within 2 or 3 minutes. So California is great. We get hot weather, but it's not very moist, and you don't have to change your shirt every 3 or 4 minutes. So wet heat is a problem. It's difficult for us to survive in wet heat. And you also get a problem, especially those of us who've got pale skin, it's harder to absorb vitamin D. And so, our skin is designed so that when sunlight falls on it, the body makes the vitamin D that we need. But if you've got a moist atmosphere, the vitamin D production is significantly less efficient. In fact, I grew up in coastal British Columbia, where it was getting more than 100 inches of rain a year. We were vitamin D deficient. My parents would give us this cod liver oil, and I remember my younger sister, she found a way, she hated those pills, so she found a way to hide them. I remember we were repairing a chair once, and hundreds of these pills fell out. My parents were not very happy to discover that, so, but there is a problem if you, and the darker your skin, the less efficient your body is at manufacturing vitamin D. So having a moister atmosphere and having more oxygen. Now this is something that when I was growing up, they had this idea we'd be a whole lot better off if we had more than 21% oxygen in the atmosphere. And so they would, if you were in a high-flying aircraft, they would pump more oxygen, and they still do that. But they now make sure that when you're in an aircraft, they make sure you get the oxygen you normally get at, say, about 4,000 feet, which means everybody's pleasant. No one's going to suffer. But I remember a time in the 1950s where fighter aircraft pilots were fed pure oxygen when they went out on their missions. And indeed, it made them sharper. And they were able to engage in dogfights with greater superiority than if they were just breathing ordinary air. Because when you breathe in oxygen, everything in your body is energized. They've now stopped doing that. In fact, they ceased it around about 1959 because what they discovered is that pilots who were being fed 100% oxygen, even for just brief times while they were flying these fighter aircraft, they didn't live very long. The oxygen made them more active, but it caused the body to wear out at a faster rate. And so, in fact, I remember a friend of my parents, he was a fighter pilot, and he was dead by the time he was 50 years of age. Basically, his body was worn out. And so, and maybe in the 60s and 70s, they had these oxygen bars. Any of you who are old enough can remember where you could go to a bar and you pay a little bit of money and they give you a whiff of oxygen. Notice today there are no oxygen bars around. They figured out that's not a good thing. Yes, it makes you feel great. As a matter of fact, Tim, another Tim in this class, who's got an 18-inch telescope, I'm hoping to get him involved in our star party, but he tells me when they go up to 14,000 feet, where you got a really clear sky, and the stars are so much more easily seen, you look through a telescope, he says, the problem is, when you're at 14,000 feet, you're oxygen deprived. And so it affects your eyes. And says, you think you're going to see all this stuff through the telescope because you're above all the air pollution and light pollution. He says, we take an oxygen bottle up with us. And we really want to see that faint galaxy, we take a whiff of oxygen and look at the galaxy. But he told me, we're careful. We don't take too much oxygen, just enough so we can see that galaxy. So, but the whole point is, And the real problem with extra oxygen, even if you were to raise the oxygen level from 21% up to 21.5%, it means that you have grass and forest fires that will burn out of control dramatically greater than if you're at 21%. So even a tiny boost in oxygen in the Earth's atmosphere means we'd have a big problem because things would just burn more easily. Not only does our human body burn more easily, but the grass and trees out there will burn more easily. Okay, well, what about larger shallow seas and smaller, more numerous continents? This is a big point in the paper that these astronomers who are saying this is all bad design were saying we'd be better off if we had larger continental shelves, because that's where all the shellfish lives, that's where all the fish lives. We would have more productivity, there'd be more oxygen pumped into the atmosphere, more carbon dioxide taken out if we had more phytoplankton in that area. And so wouldn't we be better off with a lot more continents and islands than what we have today? What they're overlooking is that thanks to plate tectonics, we have the right amount of plate tectonics to recycle the nutrients, but the plate tectonics you need to recycle the nutrients and to make sure that you have continents rising at the same rate that continents are being worn down by water and wind erosion. That degree of plate tectonic activity generates what we call the supercontinent cycle. And so 250 million years ago, there was Pangea, where basically all the world's continents, thanks to plate tectonic activity, got smashed together and formed one supercontinent. And that cycle continues, and then it winds up breaking up that. So right now we've got 7 continents. If you go back about 20 million years, there were 8 continents. We had the Indian subcontinent sitting off of Asia. It crashed into Asia, so we went from 8 continents down to 7 continents. But that supercontinent cycle, at a maximum, is going to produce 7 or 8 continents. You're not going to get 30 continents. And we need the supercontinent cycle. I mean, that's driven by the plate tectonic activity we have here on planet Earth. And so that's what's going to cause the continents to come together, break apart, come together. Incidentally, geophysicists have been able to track down 6 cycles of the supercontinent cycle. You know, what they tell you in high school is that we had just one. Pangea, 250 million years ago, the 7 continents today. The truth is this has been going on for about 3 billion years. Continents coming together, moving apart. The cycle is about 500 million years. So another 250 million years from now, the 7 continents will be one continent. Which means that right now we have the optimal level of small continents. You can't get smaller or more numerous continents than we have today without sacrificing the benefit of the plate tectonic activity. It really is at an optimal level. And you say, well, wouldn't we be better off if we had the 8 that we had? Well, it's because of the Indian subcontinent crashing into Asia that we have the Himalayas. And it's because of that crashing. By the way, it's still going on. Incidentally, it ranks as the fastest tectonic plate movement in the entire history of the Earth. When India broke off from Africa and Madagascar, it charged at a velocity of 22 centimeters per year towards Asia. And it crashed into Asia at 22 centimeters per year. When it did that, it crumpled up the ocean floor between India and Asia. Those are the Himalayas. If you want to know why there's seashells on top of Mount Everest, that's because the Himalayas are crumpled up seafloor. So it took all the fossils up with them. Incidentally, the collision is still taking place. It's now only moving 5 centimeters per year. But the 5 centimeters per year ranks as the fastest tectonic plate movement on planet Earth today. The Himalayas are getting taller and taller. So Sir Edmund Hillary did not climb the highest mountain in the world. The highest mountain in the world today is almost 2 feet higher than it was when he climbed it. And so, hey, if you sign up for a trip to go up Mount Everest next year, you will be climbing a higher mountain than people who climbed it this year. Although I don't recommend it because the oxygen there isn't very good. In fact, I've seen all the news stories how many people died this year trying to climb Mount Everest. Stay below the death limit of 26,000 feet. Okay. And then behind the Himalayas, we got the Tibetan Plateau. 1,000,000 square miles of China got pushed up thanks to this collision between India and China. What that did is it produced a third pole. And so we got Antarctica with a pile of ice. We got the Arctic ice cap. But the ice on the Tibetan Plateau in the summertime is greater than the ice we have in the Arctic Ocean. It's actually the third biggest store of ice on planet Earth behind Antarctica and Greenland. And because that ice is so close to the equator, it cools the planet 4 times more efficiently per square mile of ice than the ice we have in Antarctica or in Greenland. And if it wasn't for that third pole, our planet would be too hot for human civilization. And so, something else to thank God for. Okay, I've gone past my 30-minute limit, so I'm going to stop here. What we're going to do next week is actually get into the positive evidence for this design. And we're going to start at the level of the universe as a whole, and then we're going to go down to the cosmic web, the super galaxy clusters, the galaxy clusters. Basically going to make the point that we see overwhelming evidence for fine-tuned design for the specific benefit of humans and for the redemption of billions of us human beings at every possible size scale that scientists observe, from the largest cosmic size scales down to the subparticle level. So we're going to be taking you on that journey. So we'll start next week with why does the universe have to be as big and as massive and as old as it is? Next week. Okay. We'll take questions, and as usual, we'll alternate between people that participate here online. It's great to see all of you here, but there's way more people that participate online, so we'll be taking questions from them. They're actually with us live, and then we'll alternate with a question from people here in the audience. Sounds like we got an online question.
Yes, so first of all, I wanted to thank Nancy for bringing treats today and everyone else who brought the food. So thank you so much. You are appreciated. So our first question is from online, from Douglas McComb, who wanted to know what is the interaction or connection between dark energy and dark matter, and does dark matter have particles?
Good questions. Is there a connection between dark matter and dark energy? Well, a couple of definitions. Dark energy is the energy embedded in the space surface of the universe, and it's evenly distributed. There's no differentiation of that dark energy, and the role it plays is that dark energy acts as an accelerant on the expansion of the universe. So the bigger the space surface of the universe, the greater degree to which dark energy causes the universe to expand faster and faster with every year that goes by. Dark matter is matter that's contrasted with ordinary matter. Ordinary matter is the stuff that all of us are made up of: protons, neutrons, and electrons. It is a property that it efficiently interacts with photons. Dark matter is the opposite. It's made up of particles that do not interact very efficiently at all with light. In fact, most of them don't interact at all with light. And there's about 6 times as much dark matter as there is ordinary matter. Now, Doug was asking, is there a relationship between the dark matter and the dark energy? The answer is no. Dark energy does not engage dark matter. Dark matter has no effect on dark energy. But they both play a role in making sure the universe expands at exactly the right rate so life can exist. In fact, we're talking about fine-tuning. This fine-tuning endeavor got launched by Paul Dirac, and shortly after him by Robert Dicke. And both these gentlemen were atheist physicists, but they were the ones who were actually responsible for launching this fine-tuning argument. And it was Robert Dicke who, back in the early 1950s, determined that the rate at which the universe expands must be fine-tuned to at least 1 part in 10 to the 55th power in order for any kind of life to be possible in the universe. Expand the universe too rapidly, we'll get into this next week, but expand the universe too rapidly, you don't get galaxies, stars, and planets. Expand it too slowly, all you get are neutron stars and black holes. And it was Robert Dicke, literally 70 years ago, who calculated the degree to which it must be fine-tuned. What controls the expansion rate of the universe is dark energy and dark matter. Those are the two dominant factors that control the expansion rate of the universe. And what's even more amazing, as you're going to hear, is that it's important that the universe expand a little more slowly than it does today when the universe is young, and that it expand a little more rapidly in the future than it does today. So the expansion rate is not constant. It varies by a very tiny degree. We're talking only 0.5%, but that 0.5% must be extraordinarily fine-tuned for advanced life to be possible in the universe. Okay, we'll take a question here from the audience.
Hugh, you talked about the dangers of pure oxygen, breathing it too long. Yet there's a medical treatment called hyperbolic oxygen therapy,
Yes.
COT, where they put you in, if you have various diseases, or you have oxygen or bubble problems, like scuba divers when they come up too fast from a depth in the ocean. And they put you in this chamber and you breathe, the pressure could be 2 to 3 times an atmosphere. You breathe pure oxygen for a couple hours. And some people do this regularly for diseases that won't heal. For instance, things that are caused by diabetes or radiation therapy. So it seems to be effective. I'm wondering if it's dangerous, because Mayo even recommends it.
Okay, where you need oxygen therapy, and you're right, it is used in the medical industry. You give oxygen to patients that are oxygen deprived. So there's a number of maladies that we humans encounter where we're oxygen deprived. So for example, you often see somebody who's had a stroke or a heart attack. The people that are taking an ambulance to the hospital will give you oxygen because they know you're oxygen deprived. You do not want to give extra oxygen to people who are healthy. So, and also they're now discovering that you may want to give oxygen to certain parts of the body rather than, so I've got a relative, for example, who's got a vein problem in her legs. And basically she has a problem in the circulation of her legs. And she gets these wounds because there simply isn't enough oxygen flowing into the lower part of her leg. And there was a time when they would treat patients like that by putting them in a chamber and letting them breathe pure oxygen, or at least oxygen at a greater than a 21% level. What they've now discovered is it's better to treat the leg or the wound area. And so they'll basically, instead of putting the whole patient into a chamber, they put part of your body in the chamber, because she was getting all the oxygen she needed for the part of her body above her waist. It was below the waist where she wasn't getting adequate oxygen. So whenever she has one of these wounds, she goes to this place and they put that part of her leg and they basically feed oxygen in that area, and it helps the wound to heal. And so, yes, if you're short of oxygen, take the oxygen. I mean, if you're going to climb Mount Everest, I'd recommend you take some oxygen with you when you get above 26,000 feet, because you're going to be oxygen deprived. But the whole point is, don't take oxygen if you're not oxygen deprived.
Okay, all right, thank you.
Okay.
Hi, yeah, you talked about the necessity for tectonic plate movement and all that to distribute nutrients, and I guess tsunamis, earthquakes have this same similar purpose. So there's a need for all this, but then you have typhoons and things like that, and a lot of people die from these events. So did God mean for us not to live in certain areas? I mean, the polar ice caps are obvious, but are we supposed to be here in this state, or what? Anyway.
Okay, good question. And Okay, some reasons why you want fairly aggressive plate tectonic activity. It not only recycles the nutrients, it's responsible for driving the deep oxygen cycle and the silicate carbonate cycle and the carbon cycle. And this is stuff I've all written about in the latter chapters of Design to the Core. And so if you don't have the plate tectonic activity at a strong enough level and sustained for billions of years, these chemical cycles will not run at a rate that's going to be needed even for microbial life, let alone for advanced life. So, and that's one of the wonders of planet Earth. We live on a planet that's had strong plate tectonic activity running for over 3.5 billion years. And you need 3.5 billion years of life on planet Earth to open up a window for human life. Keep in mind, you need 3 billion years of bacterial activity to chemically transform our planet from having all the metals in soluble form, where most of them are in soluble form. If you have them all in soluble form, that's immediately poisonous to advanced life forms. So you need a long history of life, which means you need a long history of plate tectonic activity. And incidentally, that also plays a role in ensuring we have a strong enough magnetic field to protect us from deadly cosmic radiation and also from deadly solar radiation. But you're right, there are consequences. You get volcanoes, you get earthquakes. And people kind of recognize the benefit of volcanoes. When a volcano erupts, what happens? You get all this nutrient-rich dust and ash coming up. And notice how quickly people come back to volcanoes after they erupt, because they know they're going to get a really good harvest when they plant their crops. So any place where you got volcanic soil, you're going to get really good crops. And by the way, the Ice Age cycle actually drives a cycle of volcanic activity that enriches all of our agricultural plains. So people recognize the benefit of volcanoes, but they also, and wonderful thing about volcanoes too, you get a warning. And so we can ring a volcano. So for example, there is a super volcano here in California. It's that ski place. I'm trying to remember the Mammoth Mountain, that's it. It's a super volcano. And but they ring it with seismographs. Well, we know when an eruption is going to happen. They can give you about a 1-month warning when there's going to be an eruption. Mount St. Helens, they gave all the residents there a 6-week warning, an eruption's coming. You better vacate. Some people didn't listen, they suffered the consequences. Earthquakes, on the other hand, you can't predict them very well. Although there's a new technology where they think they can give you a 6-second warning of when a major earthquake happens. Well, 6 seconds is enough time to take appropriate cover, right? So, but we do need, to get the plate tectonics we need the earthquakes. But the wonderful thing is, notice that it's not, the earthquake activity is not so great that we get magnitude 10s. By the way, that scale, it's a factor of 10. And magnitude 9 is 10 times more destructive than a magnitude 8. And to put this in context, there's only been 3 magnitude 9s in the last 200 years. But a magnitude 9 will shake the bark off trees. So it's quite violent. But I remember visiting Anchorage shortly after they had a magnitude 9. And the interesting thing is there was 2 9-story skyscrapers. 9 stories is called a skyscraper in Anchorage. Not here, but there it was. They were side by side. One was totally destroyed by the earthquake, and the other one they didn't even know an earthquake was happening. So it's like, where you are relative to the shaking can make a huge difference. But in response to your comment, should we be living in California? Well, the whole point is, if you're going to live in California, take precautions. If you're going to live in Florida, where there's a lot of hurricanes, take precautions. And there's a Bible verse: don't build your house on the sand, build your house on the rock. And so don't complain about the fact that the lumber for a California home costs twice as much as lumber for a home in Kansas. We have earthquake codes, which means Your joists have to be bigger and closer together because they know there's an earthquake risk. In fact, I just discovered the home that my wife and I bought, 24 years ago. We need to upgrade it because we got a garage, a 2-car garage, and there's a bedroom and an office above it. It doesn't meet earthquake code. So we're going to have to spend some money, put some steel beams in there. But that's an example. We know earthquakes can happen here in California. They can get as high as a magnitude 8. It's wise to structure your home in such a way that you can survive at least a 7, if not an 8. And if you're going to live on the east coast of Florida, make sure your home is properly structured that it can withstand a hurricane. And hey, if you don't want to spend that kind of money, don't buy a home on the east coast of Florida. And that's a bad place to send your aged parents and grandparents and put them in a mobile home on the beach of eastern Florida. And we do that. I mean, this Bible verse, don't build your house in the sand. And what do? We put people in their 80s and 90s in a mobile home right on the beach of eastern Florida. It's a beautiful place, but you will get hurricanes. Okay, next.
Before the next question, I just want to say there's a fellow Mr. Matteo from Finland who says he's been a fan for 9 years. Hasn't been that long, so he says hi. Hello, Mr. Matteo. We have a question from the class. As you know, the magnetic poles of the Earth have switched many times in the past.
Yes.
Is there a theological reason for this?
Is there a theological reason for the switching of the poles? I don't know if there's a direct reason. We do know that if you're going to have a magnetic field strong enough to set up a magnetosphere around the Earth, basically a magnetic shield, adequate to protect us from deadly solar radiation and deadly cosmic radiation, that's going to be generated by the circulation of liquid iron in the outer core of the Earth. And then we know what causes that circulation. You can read all about it in a chapter in Design to the Core. There's actually 3 independent mechanisms that circulate that liquid iron. The moon actually plays a minor role because of its tidal forces. It's circulating that liquid iron. The other thing is the temperature differential. Our planet is such that there's an enormous, like 1,400 degree centigrade temperature difference between the bottom of the liquid core and the top. So that generates a lot of circulation. There's also a chemical factor where you have the pressure in the inner core of the Earth squeezing out oxygen and sulfur and hydrogen and carbon from the inner core and the outer core. That helps circulate. Bottom line, the circulation is complex, and therefore the magnetic pole wanders. It moves around. And hey, if you're interested, it's moving around quite rapidly right now. It used to, I remember as a child, it was situated basically in the Canadian archipelago, kind of around where southern Baffin Island is. Now it's very close to the North Pole. Hey, your compass is way better today than it was even 20 years ago. It's pointing more directly at the North Pole than it used to, because that's how much the pole has moved. And people are saying it's moving so fast right now, basically is on its way past the North Pole and heading towards Siberia. That's, just our lifetime. That's a huge amount of movement of the magnetic pole. And people can say, maybe it's going to reverse. And if it reverses, what's going to happen to us? Well, you'll find an article that I've written at reasons.org. If you just put in the search engine magnetic reversals, 2 articles I've written will pop up. But basically, that was answered by a research study which says, yes, when there's a magnetic reversal, our dipole becomes a monopole, where you get several poles. And when that happens, the field weakens. And it'll get as weak as 1/10 of a Gauss. And they say, well, if it gets as weak as 1/10 of a Gauss, won't that let more deadly radiation in? Say, how strong does it get? Maximum strength is about 7 to 8/10 of a Gauss. So it varies between that. And the reversals can last, just a few centuries, or they can last thousands of years, or tens of thousands of years. And so what these researchers did is they basically looked in the past record. Some rocks that we have recovered show the signature of as much as 16 different magnetic reversals. So they happen all the time. But what they now realize is that even when the magnetic field strength drops down to just 1/10 of a Gauss, it poses no health risks for humans. And because they've been looking for extinction events with advanced mammals with all these reversals, they can't document any. So what they're basically concluding, it's okay for a magnetic field to get weaker as long as it doesn't stay weak for millions of years. And none of the magnetic reversals last that long. So hey, if a magnetic reversal is coming, don't worry about it. It's not going to make any significant difference, but it's exactly what we expect, given the complex nature of what's driving the circulation of the liquid iron in the core of the Earth. And incidentally, you say, wouldn't it be easier if we just had one source of circulation? We need all three to get a strong enough magnetosphere. So yes, we need it to be that complicated in order to have adequate protection. Okay.
Hi, Hugh. Another online question from Chris Thompson. He says, can you please comment on this week's Nature article stating in a new study that Earth formed in only 3 million years instead of the previously thought amount of time?
Okay, I think what it's referring to, I've not read the paper. I mean, I saw it online, but I've not yet read the paper. So my comments need to be taken with a grain of salt till I read that paper. But what I think it's going to be saying is not that the Earth is only 3 million years old, it's that it formed faster than what we thought. And so this is basically back to that event where you got Theia and the proto-Earth colliding with one another and merging and forming the moon. And there's studies basically saying, it looks like the moon didn't take a long time to form, therefore the Earth didn't take a long time to form. I'm going to stop there because if I say any more, I probably am not going to get it right. So, but I'll take a look at the paper, and Chris wants a more detailed answer. In fact, what I could do is actually give that assignment to Chris. Read the paper and report back to us, just like you did, Tim. So, unless there's a volunteer in the class here who'd like to do that, that'd be great. But I don't see any challenge to fine-tuning with things happening faster or things happening a little slower. It'd be nice to have an accurate answer. For what it's worth, there's been a debate on exactly when did that collision happen. Did it happen when the proto-Earth was 50 million years old, or did it happen when it was 90 million years old? Maybe this paper gives us a more accurate answer. So yeah, I'll take a look at that. Okay, go ahead.
You mentioned earlier that the tectonic plates movements started about 3 billion years ago, I think.
Actually, earlier than that.
Okay, my question is this. Okay, now we've also been describing the movement of the core for the magnetic purposes. And I was wondering what the cause of the onset of the tectonic plates was, if we know that, and how that might be associated with the movement of the core for the magnetic, if there's some associated, or what is it that happened that caused the initiation of the tectonic plates?
Okay, I answer that question in a lot of detail in Design to the Core. And it has to do exactly how and when the asthenosphere forms, where you get that lubricant layer between the crust and the Earth. The date for the onset of plate tectonics is about 4 billion years ago. And it speeds up, so it wasn't very aggressive 4 billion years ago. It just got started, then it became progressively more aggressive. And what causes that change in the level of plate tectonic activity is what's going on in the core. So if you go back 4 billion years ago, there was no solid core. That collision basically made the Earth and the Moon hot. So both of them had a hot liquid iron core, so hot that neither body had a solid core, no solid core. The formation of a solid core played a role in accelerating the plate tectonics because you got a greater temperature gradient between the center of the Earth and the surface of the Earth. So Those factors like that explain why it has changed throughout time. And then you got the moon moving away. When the moon is close, the difference in gravitational pull on the near side and the far side of the Earth are greater than when the moon is farther away. So it also has a role to play. In fact, early in the history of the Earth, the moon played the dominant role in circulating the liquid iron inside of our core, and basically and by the way, we needed a much stronger magnetosphere in the early part of the history of the Earth than the latter part. That's actually part of what we're going to be going through in the series, why we needed the magnetosphere to be so much potent when the Earth was young than where it is today. All has to do with what's going on in the early sun.
Would you say then that the transition might be related to the formation of the solid core? I mean, that would be a fundamental change that might cause that change. And I mean, there's other factors, but that would be a large physical change.
It is a large physical change, but it's not as dramatic as you might think, because you got the interior of the Earth cooling down, and then you get a really tiny solid core forming right at the center. And that core is getting bigger and bigger as the interior of the Earth gets cooler and cooler. In fact, a professor I had in geophysics, he's famous for calculating the rate at which it cools down. And he basically published a paper saying our inner core is getting 1 millimeter bigger in diameter every year, which means within about 2.5 billion years, there will be no liquid core. It'll be completely solid. And when that happens, it's going to shut down our magnetosphere, and it's going to dramatically drop the rate of plate tectonic activity. In fact, it may even end plate tectonic activity. But the fact that we got this slowly growing solid inner core means that we have a rather gentle acceleration going on of the plate tectonic activity. And that explains also why our planet has no continental land masses until about 3.8 billion years ago. That's when you first start seeing tiny cratons, little tiny continents forming. So before that, it's a water world, just like you see in Genesis 1-2. Water covered the whole face of the earth.
That looks like that's our time for today.
Okay.
Just a reminder, next time, if anybody has any questions, you're free to ask any question on any topic about science and faith. It doesn't have to be fine-tuning. And people online were reporting it's hard to hear the questions. So if you come up here, speak real loudly, because it's hard for the mic to pick that up. I'm sorry to everyone online, the questions I didn't get to, but thank you for your questions. And Dr. Hugh Ross, would you mind closing us in prayer?
Yeah, I'll be happy to do that. And yes, I've been getting that comment from the online people. They want to hear your questions. So when you do come to the microphone, get really close to that microphone, because yeah, we're wanting to record both the question and the answer. Father in heaven, we thank you that you're the Father of all of us. And thank you, Lord, for the earthly fathers that you've given us. And Father, we pray for them today that you would help them to become like you. Lord, that you'd help them to be more Christ-like in their character, that they can help us. And Father, I pray to those of us that have fathers, we would help them by doing everything we can to manifest Christ-like character. And Lord, we thank you for the privilege of being alive in a century when so much is being discovered about your record of nature that testifies to your power, your glory, and love. Lord, may we just stand in awe of what you've done. And Father, the heavens really do declare the glory of God. Thank you for revealing your glory in such exponentially greater ways than you have in the past. And Father, I pray that we just wouldn't keep this to ourselves, but we would share it with others, that they too can see your glory and righteousness revealed in everything that you've done. In Jesus' name, amen. Thank you.